In this video, we're going to state the definition of the Riemann integral of a function. And we're talking about the definite integral, right? We're not antiderivatives. And then we're going to prove a little lemma that allows us to, in some cases, actually calculate the Riemann integral. So one reference, the reference that I'm following is the book by Rosenlicht. So the reference is the book by Rosenlicht, Introduction to Real Analysis. And I'm using the definition that's in this book. So the definition of the Riemann integral is the following. So suppose that you have a closed interval, say from a to b, and a function from this closed interval to r, okay? Then, so f in here is just any function. So f be any function on the closed interval, any real value function on this closed interval. Then we say that f is Riemann integrable on this closed interval if there exists a number a, so a real number a, such that for every epsilon greater than 0, there exists some delta greater than 0, such that if we take any partition of width delta, so for any partition of width delta, actually I think it should be width less than delta, any partition of width less than delta and any Riemann sum S associated with the partition, with such a partition, then the absolute value of a minus s is less than epsilon. So what that means is there's some number with the property that it can be approximated by Riemann sums of arbitrarily narrow width. That's basically what this is saying. So if such an A exists, we say that f is Riemann integrable. So if A exists, right? Okay, well, that's the definition of Riemann integrable. So in this case, we write the symbol, the integral of f from a to b, we define that to be a. So we call this number the Riemann integral of f. So my understanding of the history is that this is the original definition of Riemann integrability. This was Riemann's definition of what it means for a function to be integrable. The definition that you see in calculus textbooks is different. So that involves the upper sums and lower sums of partitions, and it's something like if the soup of the lower sums is equal to the infimum of the upper sums, then that common number is called the integral. And my understanding is that is called the Darboux integral. So most calculus books use the Darboux integral. But they call that function that is Darboux integrable, a Riemann integrable function, or they just call it integrable. And it's a theorem that Darboux integrability and Riemann integrability are they're equivalent. So a function is Riemann integrable if and only if it's Darboux integrable. And the Darboux integral is a bit easier to understand, so it's easier to work with, and so that's the one that you see in most calculus books. But my understanding is that the definition that I gave is Riemann's original definition. The problem with this definition of Riemann integrability is that it's hard to actually calculate what the integral is, right? It just says, well, it's integrable if there is some real number with this property that gets, that essentially it's arbitrarily close to any sufficiently narrow, Riemann sums of sufficiently narrow width. So here's a lemma that actually helps us to calculate the integral if it exists. So here's a lemma, which is not in Rosenlich's book, but I'm just going to prove it. I don't have a reference for this. So the lemma is, suppose that you know that the integral exists. And it turns out that if f is a continuous function, the integral exists. That's a big theorem. So suppose that you know the integral exists and you want to know what it is. Now suppose that for each integer n, positive integer n, there is a Riemann sum say R of n, corresponding to a partition of width 1 over n. Well, these exist in general, but the key condition is, so you have these Riemann sums and that the limit of R of n as n goes to infinity exists. And is, say, I. Call this limit I. Then the proposition is that the Riemann integral is equal to I. So what this lemma is saying is that if you can find, for each n, a Riemann sum, so the Riemann sum depends on n, and you let n go to infinity, so R of n is some function of n, you let n go to infinity and you get some limit, then that limit is the integral, if you assume that the integral exists. So here's a proof. So for simplicity, I'll just let a be the integral of f of x dx. So we want to show that a equals I. So let epsilon be greater than 0. So here's the standard analysis trick for proving that two numbers are equal, right? We let epsilon be greater than 0, and we want to show that the absolute value of the difference is less than epsilon. Then that will show that the absolute value is equal to 0, in which case a equals I. Okay, so we want to show that the absolute value of a minus I is less than epsilon, and we know that the integral exists, right? In the lemma, it says suppose the integral exists. So by the definition of Riemann integrability, so since the integral exists, so we let epsilon be greater than 0, so there exists some delta greater than 0, such that for any Riemann sum S corresponding to any partition of width less than delta, then the absolute value of a minus s is less than epsilon over 2. That's just stating the definition of Riemann integrability and using epsilon over 2, which we can do because we know, right, so we're just using the standard kind of analysis trick that if something is true for all epsilon greater than 0, then it must be true for all epsilon over 2 greater than 0. So, yeah. Okay. So we have this. Now we use the hypothesis in the lemma. So by hypothesis, well, so we have this limit exists. So the R of n's are approaching I. So for every epsilon, there exists some integer m such that for all capital N greater than m, the difference, there is a Riemann sum R of n such that the absolute value of I minus R of n is less than epsilon over 2. So that's just from the definition of the limit. And now, do you see what we are going to do? So we're going to try to combine these two inequalities. So the hypothesis says that there is a Riemann sum R of n, right? Such that you have this inequality, and then the condition of Riemann integrability says that for any partition of width less than delta, any Riemann sum S corresponding to any partition of width less than delta, then you have this other inequality. So you want both inequalities to be true, right? So, and we know that the second inequality holds for all n greater than m. So we just let n be greater than the maximum of m and 1 over delta. Then this Riemann sum R of n, okay, so if we let n be greater than the maximum of m and 1 over delta, then we know that there is a Riemann sum R of n such that the absolute value of I minus R of n is less than epsilon over 2. And then we can apply this other inequality here with S equal to R of n, because R of n will be a Riemann sum corresponding to a partition of width less than delta. Right? Because R of n was a partition of width 1 over n. So, so then 1 over n is less than delta. So therefore, okay. So, therefore, that's the value of a minus I by the triangle inequality is less than or equal to that's the value of a minus R of n plus that's the value of R of n minus I. And then this is less than epsilon over 2 plus epsilon over 2, which is epsilon. Maybe to make the proof a little better, I should have written after n greater than max of m and 1 over delta, I should have said, okay, let R of n be a Riemann sum, such that the absolute value of I minus R of n is less than epsilon over 2. I mean, this is sort of implied. So, yeah. So that proves the lemma. So let's apply that lemma to actually calculate an integral. So how would you calculate the integral from 0 to 1 of x, assuming that the integral exists? Well, by the lemma, we just need to construct for every integer, every positive integer n, a Riemann sum, and then of width less than 1 over n, and then take the limit as n goes to infinity. So here we have 0, and here's 1, and here's x. So for each n, let's split the interval from 0 to 1 into n pieces. So each width is 1 over n. And then let's just take the right Riemann sum, the right-hand Riemann sum. So this Riemann sum. Well, what is that Riemann sum? So you have 1 over, so this first area here is just going to be 1 over n times 1 over n. And then the second one is going to be, so each of these has width 1 over n, right? Each of these rectangles. So you have 1 over n times, well, actually it's 1 over n times 2 over n, because the value of x here is 2 over n. So you just plug in 2 over n here. So this is 2 over n. This one is 3 over n, etc. And then you end up at n over n, which is 1. So it's going to be 1 over n times 1 over n plus 1 over n times 2 over n plus 1 over n times 3 over n all the way to 1 over n times n over n. So that's one of the Riemann sums, r of n. And then we can factor out the 1 over n. So you get, you can actually factor out the 1 over n squared, can't you? So then you're going to get 1 plus 2 plus 3 all the way to n. And then that is going to be n times n plus 1 over 2. So n times n plus 1 over 2n squared is r of n. So that's going to be n squared plus n over 2n squared. And now we take the limit of r of n as n goes to infinity, and that's going to be 1/2. So by the lemma, the Riemann integral, the integral from 0 to 1 of x, is equal to 1/2, which is true. So that's how you can calculate some simple Riemann integrals, essentially from the definition. I mean, you're using this lemma, but the lemma follows from the definition without using the fundamental theorem of calculus. And it would be harder to calculate something like the integral of x squared from 0 to 1. But it is possible. You just use essentially the same Riemann sum, except you have to know the formula for the sum of the first n squareds. And that's, there's some complicated formula. But if you use the formula, I guess it's not that complicated, but it's kind of hard to come up with. And actually, I don't even know how you come up with it. But it can be proven by induction. There's some tricks to see where you get the formula for the sum of the first n squares. Anyway, if you do that and then you calculate the limit, you do get a third, which is equal to the integral of x squared from 0 to 1. So let's summarize what we did in this video. We stated the definition of Riemann integrability of a function. Okay. And then we proved this little lemma that is helpful for actually calculating the Riemann integral if you know that the Riemann integral exists. And then we did an example.